These notes are for the second section of Chapter 3. It's Unit 6, Polynomial Functions. In the first section, we talked specifically about quadratic functions. Those are the ones that most students are familiar with. But in Algebra 2, you also did polynomial functions. Polynomial functions have the form f of x equals, and there's a number, x to the nth power, plus another number, x to the n minus 1, all the way down to where it's x to the 0 power. You don't need to know this. You're familiar with polynomials already. So a polynomial could be f of x equals x squared plus 4x minus 7. So this n that's here would be a 2. This a sub 0, x to the 0, anything to the 0 power is 1. So a sub 0 is the last term, which is the constant, is negative 7. That's an example of a polynomial. Another polynomial would be y equals, or f of x equals, it could be 3x, and it doesn't matter this exponent. I mean, it's being a little ridiculous. We're not going to study something to the 16th power, plus something else to another power, and something else. And it doesn't have to have a specific number of terms, but if you notice, all the exponents here are positive numbers. Like this would be a 1, this would be a 1, and they're all integers. So I'll give you one more example. F of x equals 5x plus 12x to the 4th minus 6x squared minus 9. The first two I put in order from highest degree to lowest degree. This one I just showed you, it's still a polynomial. It doesn't have to be organized, but all the exponents are integers and they're all positive. To give you an example of what are not polynomials, could be something like this. F of x equals x to the 1/2. So that exponent is not an integer. Or it could be f of x is equal to x to the negative 2. That's a negative integer, negative 2. So that's not a polynomial. And another example would be f of x equals 3x squared plus 4x minus 1 over x. Well, this is part of a polynomial. The 4x is part of the polynomial. But as soon as I wrote this negative 1 over x, that stopped it from being a polynomial. When I write 1 over x, it's the same thing as saying x to the negative 1st power. So that is not a polynomial. The graphs of polynomials are very specific. All polynomial graphs are smooth and continuous. So for example, quadratic looks like this. You could have one that's got a whole bunch of wigglies in it, or another one that looks like this. All of these are examples of polynomials. Graphs that are not polynomials would be something that look like this, like a piecewise function. We've done these. It's not continuous. As soon as I had to lift up my pen to go from this part to this part, it was not continuous. So it's not a polynomial. This is an absolute value function. That is not a polynomial. We did greatest integer functions. Greatest integer functions look like this. This is not a polynomial because it's not continuous. If there's a break at all, if I have to pick up my pencil at all while I'm drawing these, it is not a polynomial. Rational functions. Like this would be a rational function. That's not a polynomial because it's not continuous. Polynomials have degrees. They have and they have names to go with those degrees. So if it's a 0 degree polynomial, it's called a constant. On the Algebra 2 SOL, you were expected to know a degree and the name that went with it. So an example of a constant would be y equals 3. And it would be a horizontal line. A vertical line is not a polynomial because it's not a function. If we had y equals mx plus b, this degree of 1, that means the largest exponent we're using is this 1. And a line looks like that. So it's a linear polynomial. If I had y equals ax squared plus bx plus c, that's a quadratic. You can have a quadratic that opens up like this, or it could open down. But now you start seeing a pattern. Let's do one more and then I'll talk about this pattern. If I had y equals 4x cubed minus 7x, it doesn't matter how many terms there are. I just look at the largest exponent. That largest exponent is the degree. So now a cubic, this is called a cubic, tends to look like this. So now let's talk about the graphs of these. A degree of 1, straight line. There's no turns. It doesn't make any moves. It just goes in the same direction. A degree of 2, turns once. So I'm going down, I turn and go up. Or I would have started going up and turn and go down. This cube, I'm going up, it turns once and it turns a second time. So now a degree of 3 has 2 turns. So can you guess what a degree of 4 has? And it doesn't matter the order I write this in. The largest exponent. So what happens, it turns once, it turns a second time, and then it turns a third time. So it's going to turn 3 times. So what happens with these polynomials of degree 2, degree 2 has a relative max or min. Degree 3 has 2 relative max or min. This one could have 3. A 5th degree polynomial, it doesn't matter anything else. I just know it has the largest exponent is a 5. And it could have 4 turns. So a cubic kind of looks like a camel. A quartic looks like a W. If it's flipped over, it looks like an M. And a quintic looks like a 2-hump camel. So anything with a degree is just called an nth degree polynomial, and it's always going to have, well, there's a pattern with it, and we'll talk about that next, but if the number of turns it can have is always 1 less than the number of degrees. So there's also a pattern with these. I love patterns. They make my life a lot easier. Odd degree polynomial. So my odd degree polynomial is like this 1, this 3, and this 5. All odd degree polynomials end up in opposite directions. And we're going to call them end behaviors. So one's going up, whatever's happening in the middle, and the other's going down. Or the other way around. This one's going down, something in the middle, and then it ends going up. Even degree polynomials, like your 2, 4, 6, if you look here, 2, they both either go up, these go up, or they both go down. So same direction for end behaviors. So they're either going to, doesn't matter what's here, both go up, or both going down. The leading coefficient, when the polynomial is written in descending order, like highest exponent down to the lowest exponent, the coefficient at the front of the equation and the degree of the polynomial will indicate the end behaviors of the graph. So if it's an odd degree polynomial and the leading coefficient is negative, then it's going to look like this. something like this, it goes down. So the left side goes up and the right side goes down. So the left side is going up. Up means f of x is approaching infinity as x approaches negative, let's get this right, x approaches negative infinity. And the right side is going down, so f of x approaches negative infinity and x approaches infinity. I'm not going to worry too much about this. I'm showing it to you mostly because you would have seen this in Algebra 2. Standardized tests might have it on it. I'm not going to use this notation. An odd degree polynomial where a positive leading coefficient, opposite directions, so the left side, f of x approaches negative infinity as x approaches negative infinity. And the right side is going up, so f of x is approaching infinity as x approaches infinity. An even degree polynomial, let's start with a negative leading coefficient. So even degree always goes in the same direction. So if the leading coefficient is negative, it's a reflection over the x-axis. It's opening down. Even degree with a positive leading coefficient, both going in the same direction, so it's going to open up. And we're going to use this to sketch graphs, and the sketching of the graphs, once you get the hang of it, is pretty easy without a calculator even. Okay. The zeros. The zeros are also called the roots, the x-intercepts, the solutions. We're going to use the zeros to help us graph a polynomial. So what you have to do, if we have an equation, y equals x squared plus 4x plus 3, we're first going to set it equal to 0. Then we can factor this. This will factor into x plus 3, x plus 1, set each factor equal to 0. So we've done this before with quadratics. And we get x is equal to negative 3 and x is equal to negative 1. Those are our solutions. I'll give you 4 examples. If I had a function where I had 3, x plus 7, x minus 4, x minus 5, and this equals 0. This is already in factored form. There's no purpose at all to multiply it back together. Leave it the way it is. Set each factor equal to 0, and I get x is equal to negative 7, x is equal to 4, and x is equal to 5. Let's try another one. What if I had x squared minus 9 and x squared plus 3 equals 0? Well, x squared minus 9, set that equal to 0, I get x squared equals 9. Take the square root of both sides, but as soon as I take the square root of both sides, I'm going to have a positive and a negative, so I get x is equal to plus and minus 3. This x squared plus 3 equals 0. I get x squared equals negative 3. Take the square root of both sides, I get plus or minus I square root of 3. So this solution, there are 2 real solutions and 2 complex solutions. And one more example. Say I had 5x squared minus 10x equals 0. I can factor greatest common factor. So 5x equals 0. X minus 2 equals 0. Divide by 5, you still get 0. Add 2, you get 2. So now to use these to graph. Well, let's talk about the multiplicity. I almost forgot about the multiplicity. The multiplicity is how many times a particular 0 is used. So if I had equation y equals x plus 1, x minus 3 squared, and x plus 5. The multiplicity, negative 1 has a multiplicity of 1. It's used once. Three is used twice. It's squared. So its multiplicity is 2. And then negative 5 is only used once. So it has a multiplicity of 1. If I had 2x, let's make this 6x minus 1, x plus 3, and x minus 4. Let's make this to the 4th power. So I have 0 used once. I have 1/6, 1 divided by 6 used one time, negative 3 used one time, and a positive 4 used 4 times. So the multiplicity is how many times it is used. Sorry, I didn't realize I hadn't picked that up. So now I'm going to do several examples of graphing these. And I don't want you picking up a calculator to graph it, not just because I'm mean. It's because a graph from a calculator can distort it. It takes more time to put this in a calculator and graph it than it does just to work it through. So let's start with, let's have this one, y equals x plus 3, x minus 4, x plus 5. So what I would want to do is I'd need to figure out the degree and the leading coefficient. So my degree, if I were to multiply this all together, x times x times x, I'll get an x cubed. So my degree is 3. My leading coefficient is positive. And I'm just going to say a greater than 0 because math people love initials. My zeros, I get negative 3 used once, 4 used once, and negative 5 used once. So I'm going to just draw a number line. I'm not going to worry about putting all the numbers on it. I'm just going to put the ones I need. I'm going to mark all of these. So this is a degree of 3. It's an odd degree, so I know it starts down here. It's going to end up here. It's got to go through all 3 places. So it's going to have 2 turns. It's going to turn this way, and it's going to turn this way. But it can only go through these 3 points. So it's just going to do this. And I don't care how high or how low. That's why I don't want you picking up a calculator. I just know that it's going to have this general shape, and this is what it's going to look like. We'll see how many I can get on this page. Let's do another one. Okay, so I'll look at this one. The degree is 2. If I were to multiply this together, I get something x squared. So my degree is 2. My leading coefficient, I have a negative in front. So if I multiply this all out, it's going to get a negative x squared. So my leading coefficient is negative. And my zeros are going to be a positive 3 and a negative 1. So I'm just going to put those numbers there. I don't care about the other ones. Now think about this. A degree of 2 is a quadratic. I know quadratics. I've used them often. So it's a negative leading coefficient. Instead of opening up, it's going to reflect over the x-axis. So it's going to look like this. So when I make these values at negative 1 and 3, it's going to just look like that. Just a quick sketch. I don't care about the height. Let's do y equals, let's do the same kind of graph, but let's put a negative, x minus 3 squared, x plus 1. So what I changed is I now have a multiplicity of 2 on this. So that means if I multiply this all out, I'm going to get an x cubed. So my degree is 3. My leading coefficient is negative. And my zeros are 3. It's used twice, so I'm going to actually write it twice. It helps me when I draw this. And then negative 1. So I know the shape of this. It's going to look like this one here did, but it's going to be reflection over the x-axis. So it's actually going to start up here, come down, turn, go up, turn, and come back down. So when I draw the number line, I mark the same points as I did on that last problem, but it's not going to look the same. I've got to show that this 3 is used twice. So what happens is, I know it starts coming down, and it's going to turn and go back up. But because this is used twice, it bounces right off, and it's going to keep going down. So it has the correct shape. It touches the x-axis at all the zeros, but it only goes through here and bounces off here. Anytime you have a multiplicity that is an even number, the graph will not go through it. It bounces right off of it. Anytime you have a multiplicity that's an odd number, the graph will go through. Let's pick another one. Let's do y equals 2x, x plus 4 squared, x minus 2 squared. Okay, so I've got 1, 2 more here, so that's 3, 2 more here, so that's 5. So my degree is 5. My leading coefficient is positive, so I know a is greater than 0. And I know my zeros are 0. Don't forget this 2x. This x means it's got to have an x-intercept using that x. Negative 4, I'm going to write that twice. And 2, I'm going to write that twice. So 2, 0, and negative 4. And it helps me if I go ahead and think, okay, so it's an odd degree polynomial with a positive leading coefficient. It's going to start down here and end up like that. It's going to go through, okay, the negative 4 has a multiplicity of 2, so it's not going to go through it. It's going to come up, bounce off the negative 4, turn, go up through the 0. It's going up through the 0 because that's only used once. And it's going to come down, touch, it's used twice, so it's not going to go through. It's going to turn and go right back up. And I could do hundreds and hundreds of examples. Let's just do 2 more. So let's pick, let's do y equals x to the 4th minus 81. This can be factored. This is a difference of squares. So let's go ahead and factor it. So I get the square root of x to the 4th is x squared. The square root of 81 is 9. So I'm going to get x squared minus 9 and then x squared plus 9. Well, we did x squared minus 9 before on the front hand side. If I do x squared minus 9 equals 0, I get x is equal to plus or minus 3. If I do x squared plus 9 equals 0, I get x squared equals negative 9. So x is going to equal plus or minus 3i. Now that's different. So let's look at the degree. Our degree is a 4. We have a positive leading coefficient. And my zeros are 3 and negative 3. I can't graph 3i on a number line. So I don't even need to know those right now. So I know when I do my number line, I'm only going to mark these 2 points. With an even degree polynomial and leading coefficient positive, I know it's going to end up at both ends. Both ends are going to go up. And it's going to look like a W because it's a degree of 4. So the way I do that is I'm going to come down. It's going to turn, but look at this. It doesn't go back up through there. It turns before it reaches the x-axis. And then it comes back up here. And the last one I'll do, let's do y equals 16 minus x squared. So I can factor this. I get difference of squares, 4 minus x, 4 plus x. I'm not going to change that around. I could. If I changed it around, it'd be negative x squared plus 16. I would factor out a negative 1, and I get x squared minus 16. And then when I factor, I get negative 1, x minus 4, x plus 4. That is okay to do. If you change it around, make sure you factor out the negative. But here, if I let 4 minus x equals 0, I get 4 equals x. If I let 4 plus x equals 0, subtract 4, I get x equals negative 4. So my degree is a 2. My leading coefficient is negative. This negative is in front of the x squared. So a is less than 0. And my zeros are 4 and negative 4. You can make those points. This is a quadratic, and I'm very familiar with quadratics. You've used them since Algebra 1. So quadratic opens up, a parabola opens up, but it has a negative, so I know it's got to do this. So all it's going to do is look like this. I like this section. When I would teach Algebra 2, I could get students to pass SOLs easily with this unit here, because there's a lot of information on this unit. It's not difficult, you just need to practice it.